I don't know if anyone else.
Okay, started recording.
Let's wait for 5 more minutes then, just to.
Okay, then let me stop recording then. Just okay, I started the recording again. You can take it away.
Yeah, I'm just trying to find the window that I want to share. Share. Okay, before I start, I guess I should do a short introduction. So I don't know how is everyone familiar with what the general approach is, but briefly, the approach that China, okay, let's not say China because no one knows what they did. Approach that Singapore and South Korea did was to have a mobile app which tracks interactions through Bluetooth, GPS, Wi-Fi, whatever. And once someone is recorded as infected, they go through their previous interactions and backtrack all of the people who might have gotten an infection from that person. And this is a so-called direct contact tracing, in which only direct contacts are accounted for. No multi-step propagation through the network is made, which means that if I am infected, people who I met will be notified and will probably go into self-isolation, but all of the people who met those people won't know anything about it, which is especially the problem with this infection because there are so many asymptomatic cases, with the report from Iceland saying it's 50% and so on. So this means that a lot of these people who are in my neighborhood, who by neighborhood I mean the social network neighborhood, so people who I was in contact with, most of those people, 50% of those people, won't have any symptoms, and after 5 days they'll say, okay, I don't have any symptoms, I'll go to the store, I'll go, and so on. And then all of the people they meet will never know that they were in contact with someone who was in contact with someone infected. Because this virus is highly spreadable, as we can easily observe, such multiple step transmissions are very frequent, and it is a big benefit if we can predict those multi-step transmissions, and if we can somehow calculate for each person what risk they have of having this illness, not just from their direct contacts, but from the whole cluster in which they live in. Now, I will go through the short presentation that I just shared with Andre, just so we are all on the same page regarding what data do we have, how do we collect it, and how does the general problem that we are trying to solve look like. And then I'll go through the results. Then I'll go through the explanation of how the model works and through the results of the model of the simulations that I have been running this past week or so to try to estimate what the real benefits of this model are. So I'll share the screen now. Can I share the whole? Yeah, I can. Sure. Do you see my screen?
Yeah.
Okay, so infection risk estimation, distributed propagation-based approach. So first of all, what is the data that we have? This is all of the things that you probably already know. We have a temporal interaction network. Temporal means that it has a time dimension. It's not only a simple graph, it's not only a simple network with nodes. So nodes are people, and what we call the interactions in graph theory and in network science are edges. So maybe I say edges sometimes, and so don't let me confuse you. So these edges are these interactions that we detected and have stored, and nodes are the people, or more generally, nodes are devices which detect these interactions. There is a time dimension, which is why we call these networks temporal. So each moment device can transmit to our servers the information about the proximity network that it detects. In other words, the number of and the IDs of nodes that it can detect in its physical surroundings. And each such interaction, apart from the timestamp that it occurred on, can also have some kind of weight, maybe the closeness of the two nodes, physical closeness, or maybe the duration of the interaction, and so on. But we won't go into these parameters at all today. So these are just additional things that we might use at some point, but even without them, our models are quite good. So let's just stick to the simplest possible model. And apart from those interactions, we also have the reported infected nodes. So whenever someone is tests positive or has some clear indication, some clear symptoms that show that they probably have the illness, that they're probably infected, we get those pings to our server, and we know, of course, with some important delay in time, in terms of days before the symptoms onset, we know who is infected. From that, we can also estimate when were they infected. So if your symptoms started now, we can estimate that you probably got infected sometime in the past 5 or 10 days. Now, the baseline approach that I just mentioned, that is used in Korea and in Singapore, and maybe in China, who knows, is that you detect and collect contacts. So you gather those interactions. Whenever the interaction is reported, you try to estimate when this infection really occurred. And then for each interaction that happened after this estimated time of infection, you notify everyone who was in contact with this person, and you send them a message saying, you were in contact with XY, they're infected, please go into self-isolation. As you can see in even this simplest approach, in this simplest example, we have this node who was, do you see my cursor, my mouse? Okay, you have this you have this node that was infected. It was in contact with this node here, so we notified them. It was in contact with this node here, so we cannot notify them, but we never notify this node here, who was in contact with the second node that was that probably was also infected. This is the problem that you are trying to solve. So this node here, this leaf that we can see right here, is the idea, is the goal of this model. Propagation-based approach is the same in terms of detection and collection of contacts, is the same in terms of estimation of the general time when the infection started, but is different in the way that we use the data to propagate through the network. Okay, I haven't colored the node here. Anyway, as you can see, because this node here got notified, we will also probably notify this node here. Now, of course, we won't go through the whole network because that won't make sense. Then we will just get notifications for everyone. We have to find some smart way of ranking all of the nodes to see which nodes are at the top of the risk, which nodes should get the notification, although they maybe weren't in the direct contact with someone who is reported as infected. So from now on, whenever I say notified, I mean predicted as infected in our model. And I presume that we already notified all of the people who were in direct contact with the infected. So this baseline approach in the previous slide is always used. We just notify all of people. But then we want to see additionally how much benefit do we get by taking all of those other nodes aren't. Sorry?
They weren't other.
Yeah, I muted Annie. There was some noise. I muted him. Go ahead.
Sorry. So all of those other nodes, we take all of those nodes who weren't, first of all, infected or reported as infected, and second, who weren't in direct contact with the infected. We take those other nodes and we try to rank them in some way and then say, okay, let's now push the notification to the top 10% of these nodes and say, you have a high risk of infection, try to isolate or whatever you think is the best thing you can do. Now, why do we do simulations? Why can't we just propagate the probabilities? So the approach that first comes to mind, and in general people start with and Andre started with, which is very intuitive and seems like it would work, is the approach where you just take a node, let's say an infected node, you say, okay, this node has a probability of 100% of being infected because it is infected, it tested positive. Then, because the transmission probability is, let's say, 50%, all of the nodes that it was in direct contact with are now infected with probability of 50%. Then all of the nodes that they were in contact with are now infected with probability of 25%, and so on and so on. If someone was in contact with two people who are, let's say, 25%, have 25% chances of being infected, then their combined probability for me would be something like 32% or whatever the max is. The problem with this approach is that it just doesn't work because the problem of estimating these probabilities is basically an intractable problem. And well, instead of me just trying to theorize now, I think the example is much better. So let me go through an example. As you can see, this is a node that was infected, this red one, and its probability of being infected is 100%. Node A was in contact with this infected node, so their probability is 50%. Each of the next four nodes, B1, 2, 3, and 4, was in contact with A, so their probabilities are 25%. If anyone has any questions, just jump in and stop me. So their probability is 25%. Now, if we wanted to calculate what the probability of C getting an infection is, we could say, okay, probability of C getting an infection is 1 minus the probability of C not getting an infection. That's how probability works. And C not getting an infection is just a multiplication of the probability that infection didn't pass from B1, that it hasn't passed from B2, from B3, and from B4. This joint probability is 1 minus P to the third and then to the fourth. I should have probably written this out a bit better. Is anyone confused with this number?
No, it makes sense to me. This was the flaw in the model.
P to the third is the probability that B1 is transmitting the disease to C, because probability of infected node transmitting to A is P, A to B is P squared, B to C is P to the power of 3. The probability that it did not pass this infection is 1 minus P to the third, and then the probability that it happened here, and here, and here, and here is 1 minus P to the third times 1 minus P to the third times, etc., and then 4 times that, and you get 61%. Basically, you can just intuitively see that node C has some higher chances of being infected than node A with this simple propagation model. But that obviously cannot be true, because for C to be infected, A has to be infected too. A is a prerequisite, because if A wasn't infected, no infection could propagate through the network further, and C wouldn't be able to get infected. This is a contradiction, because if A is a prerequisite to C, the probability of A getting infected has to be higher than probability of C getting infected. Because probability of C is higher than A, we have made some kind of an error. This can be generalized further, but I think this intuitive example is the best way to see why such an approach won't work. So what can we do about that? What can we do about that is that we can run simulations. We can say, okay, let's start with a simple infected node. Let's flip a coin and say, okay, if it's heads, this node will infect node A. Then if it's heads, A will infect node B1, etc., etc. And then we will see, did node C get infected at the end of this game or not? And we will just get an output which is either 1 or 0, true or false. if we now run this simulation for 1,000 times, we would get some number of truths and some number of falses. And that amount of simulations in which C was in the end infected is basically the probability of C being infected. This is a very simple type of what's generally called Monte Carlo simulation, where you cannot really calculate some probability, but it's very simple to just simulate it 1,000 times and then say, okay, out of 1,000, I rolled the dice 1,000 times. I got 6 100 times. That means that getting a 6 is a 10% probability. How do we run these types of single simulations? So these simulations that we now want to repeat 1,000 times, how do we run them for just one time on this distributed network? Because keep in mind that all of the data that we collect is only stored on the devices themselves. When I get in touch, in contact, in physical proximity of someone else's device, my device stores this information, their device stores this information, but this information, this interaction data is not stored on the server. So we don't have a way of running these simulations on a centralized machine where we can just see all of the interactions, the whole network, and just propagate stuff, just as I explained now. We need some way of running it in a distributed fashion. We need some way of running it on the devices themselves. Luckily, this is not really a hard thing to do. We just simulate basically what the virus does itself. So all of the interaction data is stored on the device. You can see here an example of such interaction log for one node. And as I said, additional information can be stored for these interactions, weights, durations, etc. But we won't go into that right now. Then the server periodically sends some type of a tick, some type of notification to all of the devices, which says, okay, simulation 1, 2, 3, 4 is starting. The start time was this. It will end at this. If any device is offline right now and comes online in 2 days, please don't try running this simulation. It has already ended. And it also contains some additional parameters which control the simulation. Remember that first of all, we don't know exactly what the transmission probabilities of this virus is. Second, there is no single number that can tell us what this transmission probability is. This transmission probability depends on how close you were, how long were you in contact with the person, how much was this person spitting while they were talking, was it a humid area, was it dry area, what the temperature was, and so on and so on. So we have no idea what the exact probabilities of these interactions are. We can just generalize them and say that, okay, they're in general something. That something is a variable that we can tune for our models. And it is in general very important to run multiple simulations with different parameters, just in case one of these parameters produces some kind of an edge behavior that we don't want to model. So server sends the information to all of the nodes saying simulation something is starting right now. Here are the parameters, start. Now, on the other hand of that communication, nodes receive the information about the simulation starting. And we can also have multiple simulations overlapping in time. So server can send 10 different messages with 10 different parameters. It doesn't matter. So for each of these simulations that has started, nodes receive the message and then start the simulation. Simulation runs between devices through a messaging service that we have to deploy on our servers. Sadly, there seems to be no clear way of running these simulations on any kind of a peer-to-peer network, because having a peer-to-peer network on mobile devices is still not something that can easily be done. So messages pass through our server and devices can communicate. What are devices communicating? Basically, each device that is infected sends the infection message, infection information to all of the nodes that it was in contact with. But it doesn't send it directly. It sends it with some probability p, which is the transmission probability that the simulation has set. So each device flips a coin and says, okay, if it's heads, I will send this infection information to the node A that I was in contact with. Then it flips the coin again. If it's heads, I will send it also to the person B. If then it's heads, I will send it also to C, and so on for all of the interactions that occurred after the estimated time of my infection onset or incubation period onset, or whatever you want to call it. When a node receives such an infection information, such a message containing your infected content, it then sets its internal state to infected. This infected is only for this current simulation. It's not, of course, this person is not suddenly infected in real life, nor is it suddenly infected for all of the simulations that we run. It is only infected in this simulation that is being executed right now. And if it is really infected, if it has received such a signal, it just repeats the same procedure for all of the nodes, for all of the interactions that occurred after the interaction that just infected me. I will send the infection information with some flip of a coin.
Ivan, if I can just interrupt you for a second. So can you also include, when you are describing the process, can you also include what communication is happening through the centralized server and the node themselves? For example, when it flips a coin, that coin is, the operation of the coin is done on the device, but
yes.
the queue, it gets the queue to flip the phone from our server. Is that correct so far?
Yes. Yes.
Okay, then it flips the coin on the device, and it does that through the stored log of interactions for each of the nodes that it interacted with. That's correct?
For each of the interactions that it had. So if there was
Yes.
a node that it had multiple interactions with, it would do it multiple times.
I understand. So for each of just the direct interactions, and then the result of that, does that get broadcasted back to our server so that it can be then sent to the next degree of contact to perform the...
Each coin that landed heads for some interaction X to some node A, okay? So there is a list of interactions.
Yes.
We are now on this interaction, which was interaction 3 days ago with node A. Okay?
Yep.
If it flipped to heads, this node will send a message directly to A saying, I am infecting you over interaction X.
Through our centralized server.
Yes, because messages have to pass through some kind of a server. There is no direct way to communicate between devices.
And then the process will continue there with all its nodes on the A node.
A node will then try to figure out what to do with this. Okay, so now if everyone is on board with the way we are doing these things, I will now go through the real reason why we are chatting today. So I worked on this model, on this spread simulation. I mean, it's a very standard thing in epidemiological research. But the main issue that I had with it, and the main issue that everyone who I talked to had with it, is that it's very hard to to confirm that such a model would really be a good prediction of the real infection in the real world. It could be that the infection is spreading just too randomly through the population, that so for example, if everyone is in contact with 1,000 people each day and there is a low probability of transmitting the disease, you cannot really do anything with it. You know, there are too many possible paths this infection could go through, and simulating those paths would just generate random numbers, basically, would just generate some kind of a normal distribution through the whole network of how each node is, how much is each node is susceptible. However, nodes that are occurring right now, and in general, physical contact nodes, are not that random. They are, first of all, highly clustered. There are tightly knit communities in those networks in terms of families, workplaces, parts of the city, people shopping in the same store, and so on. Second, they are much sparser. You don't get in direct contact with 1,000 people each day. You get in direct contact, and indirect contact in the sense of that the disease could have been spread, or you get with maybe 10 people each day. I'm not accounting right now for the possibility of disease getting transmitted through objects. So someone touching a doorknob and then you touching a doorknob and touching your face. That's something that I don't see a way of modeling in general. That's something I don't see a way of us solving. So I won't even be concerned with that. But what we are concerned is these detectable human-to-human interactions. Now, to analyze how well our model performs, as I said, the whole performance of the model would be in terms of what is the added benefit on top of direct contact tracing, on top of just notify everyone who was in direct contact with the infected person, which we should always do. I think this always has to be implemented. What is the added benefit of then also notifying people who are 2 steps away and higher or lower risk? I posted all of this code, so if anyone wants to go in detail through the code, through the way the notebook is set up and so on, I mean, the code is in the same folder. It's infection model repository on our GitHub. Go through it. Hopefully I commented the code enough so that you can read through what's going on. I won't go through the code now. In general, it simply simulates everything I just explained. The main question is, what type of network are we simulating it on? There are no good data sets, real world data sets about proximity networks. The biggest proximity network data set that exists is 200 and something nodes, which is basically nothing. I mean, we can draw such things ourselves. There are no large scale data sets of these things. Apparently, BBC ran a documentary where they had a similar app to ours and tracked over 10,000 people across UK, and they have that data set. Why that data set isn't published, I don't know, but we don't have it. What we can do is generate random networks. Random network generation is basically a science of itself, a very broad and complicated thing. But the general idea, what you should be aware of, is that the most simple network is the completely wrong network for us, but is also the best network to start with, just to understand how these things work. The most simple network that we will tackle is the so-called Erdos network, which is a model which takes n nodes, let's say 1,000. So this is created here, a graph or a network with a Erdos Renyi model with 1,000 nodes, and with some probability, 5%, which says between each pair of nodes, with 5% chance, create an edge, create an interaction. This produces a completely random network. There is no correlation between edges. There is no reason to believe that if I am connected to node B and you are connected to node B, that two of us are also connected, which is something that is a very strong effect on real world social networks, because a friend of a friend is also probably my friend. There is no clustering. There is no community structure. And also the average length of the shortest path between two nodes is rarely higher than 2. Because the network is so randomly connected, it's always possible to just jump around in any way and reach every node. Because of this, this is a completely wrong model for what we are trying to do. But on the other hand, it's a model that can be very easily modeled. It can be solved by basically a differential equation. And in physics, they very frequently use this model for different types of things. It has some really nice properties of being solvable. Another thing that we need to decide on, of course, we need to decide on what the, so let me just go through the parameters quickly. What is the initial percentage of population that is infected? What is the infection probability, the probability of infection getting transmitted through an interaction? What is the time of the recovery? And what is the, let's say, width of the time of the recovery? Or in this case, I modeled the recovery as a normal distribution, as a Gaussian. So this is the mean and the standard deviation. So most people would get well after 14 days, some after 13, 15, all the way to 8 or something days and so on. Thing that we also have to choose is starting from this static network, starting from this network which doesn't have a time dimension. How do we create that time dimension? First presumption that we can make is that we don't need a real temporal network, because we don't need ever to transmit the infection over two edges on the same day. What this means is if A infects B, that same day B cannot infect anyone else. It needs at least a day to become infectious itself. Okay? This means that we can basically, instead of having a timestamp, a continuous timestamp for each interaction, we can just bin them by days. And for each day, we only do a single step spread. Then second day comes, we do a single step spread, and so on and so on. Does that make sense? Okay? Okay. The question is, how do we create those daily snapshots of our network from the static network underneath? Because we don't want to just copy it over, because it doesn't make sense to presume that you have the exact same interactions each day with people. You have different interactions. We do this by first assigning some probability, some number from 0 to 1 to each of the edges in this static network. We call this probability the frequency. And then, based on that frequency, we sample edges from the network. Based on that frequency, each day, we say, okay, this edge has a frequency of 50%. That means that I will flip a coin which is 50-50, and if it's heads, I will take this edge for today. I will use it today. I can also use it tomorrow. I can use it every day, but today I will use it. This other edge maybe has a frequency of 10%. So I flip a 10 versus 90 coin. If it's in the 10 range, I will use this. If it's in the 90 range, I will not use this edge. This is the way we produce the daily snapshot of our network. Does that make sense?
So you're basically randomizing the weight of each edge.
It's not the weight, because after we have after which we choose to use this edge, we forget about this weight information. It happened. It doesn't have any additional effects on the spreading of the virus. It wasn't a closer interaction. It wasn't an interaction that lasted longer. It's just this frequency is only used to say in what percentage of days did this interaction occur. So for example, if you are living with someone, this frequency would be 100%, because each day you see them, you have interaction with them. If this is someone who works in your local store, then it's probably 1/3 if you go to the store every 3 days.
Yeah,
okay,
makes sense. Yeah.
Now the question is, again, next question is, okay, how do we assign these random frequencies to edges? We have to have some underlying distribution from which we sample these numbers, okay? And for start, we just do it in a uniform way. We just say, okay, everything from 0 to 1 is of equal probability. Some edges are 10%, some are 20, some are 30, some are 40, 50, 60, 70, 80, 90. We have the whole range. This, of course, isn't really the case in real world, because the case in real world is kind of bimodal. There are two big clusters. On one hand, you have your family and people who you live with, who you meet every day. And then on the other hand, you have everyone else who you meet rarely. There are very few people who you meet every second day. There are very few people who you meet every I don't know, third day. Okay? Does that make sense?
Yes, so you have your regular contacts, then you have some people who you meet more rarely. Those could be people at work, or maybe your friends. And then you have some people who you meet even more rarely. Those could be people who you shop from, for example.
Yes.
And then you have people who you only meet once if you happen to travel on the same bus.
Yeah, exactly. And to model this, I will come back to this later. So for now, we just use the uniform distribution. All of this that I'm saying now is something that we won't care about once we start the real thing, because then we will have real data. We will have edges coming to us from the mobile devices. This is only to make you understand on which presumptions are we running these simulations to say that our model makes sense or not. Once we start the real thing, all this is forgotten. We start the real thing, and then we can see if we really are successful or not. But we cannot really start the real thing without any evidence that we will be successful. So this is this evidence. Now, with this simple Erdos Renyi network, which is a completely random graph, we run our simulation. We run it with the infection probability of 1%. Initially, 5% of people are infected, 14 days to recover with a standard deviation of 5. There are 1,000 nodes. Each pair of nodes is connected with a probability of 5%. And then we sample from that network uniformly. So some nodes would get to be used each day, some nodes would get to be used never, and so on. We run that simulation, and we run it for 40 days. And we are running 100 simulations in parallel. So that vector is 100 bits long. The simulation detected that after 35 days, no one was infected. And by no one, I mean in none of the simulations, none of the nodes were infected. So in none of these 100 simulations, none of the 1,000 nodes were no longer infected. They were either removed or recovered, or they never got the infection. Okay?
So we would need to tweak the network.
We don't. Let me plot how it went. So you see the infection happened and then it died out. Of course, this was a very quick infection. I mean, it lasted only 25 days, 30 days, but this is on a very small graph. So this is only 1,000 nodes. Okay, so it's understandable that it lasts for a short period of time. You can think of all of this as just a simple to compute, downsampled a simple to compute subset of the problem that we will encounter in the real world. Okay, so just a smaller play, a toy example. And once we have this, we run the performance analysis. And what the performance analysis tells us is the following. First of all, it tells us what is the performance of the direct contact tracing. So what all of the other apps are doing. And it's important to say that this performance is calculated on day 4. So somewhere here. So we started with some first initially infected nodes, then we let it run for 4 days, and then we said, okay, how did we predict what will happen after 4 days? Okay, so all of this, the rest of the network is played out to see how the infection went, but it's not used in the analysis because we have to have some stop at which we reevaluate how we are performing. We see that after these 4 days, based on the initially infected nodes, if we just notified everyone who was in contact with those 4 nodes, in those infected nodes through the period of 4 days, we would notify 570 people. And out of those 570, 44 will be infected, 530 won't. And we would miss to notify 14 people who were infected. On the other hand, if we additionally on top of that added our model, added the simulation and ranking of nodes based on those simulations, we would find that additionally we were able to notify 51 person, and out of those 51, 4 were really infected. These results are extremely bad. I mean, it doesn't make sense to build this whole big thing just so we can catch 4 additional nodes, because by just improving the Bluetooth thing, we would probably catch more than 4 additional ones. But this is why this Erdos-Renyi model, this simple network model, doesn't make sense. On the other hand, let's say that, okay, I will skip through this part now because it's not that important. On the other hand, let's say that, okay, I should reorder this notebook, but basically, let's say that we don't have the Erdos-Renyi model, which is all interconnected and paths are short and so on. Let's say that we have a very unnatural, very artificial example, but a good example of what happens when the network is highly clustered. And something that basically happens when we are in a lockdown situation. This is a ring of cliques network model, and it's really, really artificial. It looks like this. Basically, clique is a fully connected subgraph. So a couple of nodes which are all interconnected to each other. You take n of these cliques of size k, okay, and you connected them into a ring. So here, each clique consists of 6 nodes. Here, each clique consists of 10 nodes, and so on and so on. You can think of this as a neighborhood. Each of these cliques is a home where some people live, and then they have some random interactions with their neighbors. It makes sense as a model. It's a very simple thing. It's a highly constrained example, but it's useful to see what happens on the other end of the spectrum of these types of networks, so that we can get the idea of what will happen somewhere in between where the real world is. When we run this, we are now running it with the very big infection probability, because this network is so sparse. The connections are so rare, so that we have to increase the probability of transmission. We see how the model went. It went good. I mean, it looks like some kind of a real infection going through the network. But now, when we run our analysis, I will just decrease this. So the number that I'm playing with now is the number which tells us what is the what amount of the topmost ranked nodes are we notifying. So I said notify the top 7% of the nodes. If we notify too many of them, then we just notify too broadly and we have too many false positives. So I just tweaked it a bit, and we see that, okay, the original approach, the baseline approach, notified only 100 people and 88 were infected. Okay, great. But additionally, our approach notified additional 325 people, 26 people. Out of those, 200 were infected. So we basically more than tripled the amount of identified infected users, which is a great result. So compared to the previous one, you see how important the structure of the network is.
So in the when we go just 1 degree of interaction, we miss 210 infections here.
Yes, exactly.
And with the multiple degrees, we just miss 9.
Exactly.
And if we were to increase the yeah, that number, we could get like
would notify too many people.
We would notify.
So we have to everyone, because everyone is at the top 8%, because after 8% everyone has the same rank, which is probably 0. So this is something that we can tune easily and automatically. I just didn't have time to code it.
So basically, that's the setting that we would work with to get some sort of balance between people who can actually go to work and produce some goods and services, and people who should be advised to not do that. I understand.
I don't know if you guys have any experience with ROC curves. Basically, what they tell you, let me go to this example that we already saw. What they tell you is, depending on how you set this threshold, what is the number of true positives compared to the number of false positives. So the number of true positive is this number here, false positive is this number here, okay? And you see that this red dot is where we currently are, so at 10%. So we notified 47 out of 380 people. So we notified a little bit more than 10%, which we shouldn't have. So this is the false positive rate, it's at 10%. And we notified 4 out of 14 people which were really sick, which is roughly 30%, which is here. So it's at 30%. This red dot is a visual explanation of this table. Okay, makes sense? Okay. And in this case, you see that this ROC curve is basically straight up and then right, which means that there exists some threshold here, which we are very close to right now. We can even increase it a bit further, which is almost at 100% true positive rate and almost at 0% false positive rate, which is ideal. I mean, this is what we want. Okay. Now, this is a very artificial example, as I said. Now, I will just introduce back that notion of the distribution of the sampling of edges, because we don't want it to be uniform. We want to have some kind of a distinction between family on one hand and all of the rest of the world on the other. For this, I created a distribution which I would call B beta, which is a bimodal beta distribution. If you want to learn more about beta distributions, I suggest just Googling and reading about them. They're basically a very simple model to get any kind of distribution with just 2 parameters, and it's great. And here I just used 2 of these distributions and overlapped them over each other. So there is one distribution on the left and one on the right. This is the small amount of people who you meet regularly. This would be your family. So a small amount of edges would have a probability of being sampled close to 1. And then a large part of edges would have a probability of being sampled at almost 0, with some going here into the 20 or 30%, which is roughly what we experience in real world. Playing with these distributions doesn't affect the model that much. So if this is unclear to you right now, doesn't make sense. It's mostly to prove to myself that these types of things don't play that much role. Anyway, let's go further. This is the model of random networks that is probably the most popular model in social science. It is also a model that a lot of people are becoming more and more convinced, myself including, is quite a wrong model for social networks, but it has some properties that really match social networks and is still really used. Anyway, this model is a model which is part of the big group of models called the preferential attachment models, which basically says the following. If you have a network where some nodes are very popular, let's say, have very high degrees, have very large number of connections going out from them, and you have some nodes which have very low degrees, have very low number of edges going out from them, which is roughly what happens in society. You know, you have people who know everyone, and you have people who know no one. Then, if you want to add a new node to this network, there is a bigger probability that this new node would be connected to the one of the popular ones than to the one of the less popular ones, which makes sense. This is roughly what Facebook looks like. This is roughly what Twitter looks like. This is why basically this model gains so much popularity, because it's great for modeling online social networks. It's not that good for modeling real world social networks, but it's good enough. So we will go through it. This is basically somewhere in between those two extremes that I showed you so far. We now have 100,000 nodes. Because this simulation takes 2.5 minutes, I won't run it again. You will have to trust me that I didn't lie here. We simulated for only 6 days because we are only really interested in how do we perform predicting things 6 days into the future. Because further than that, we will learn new information. We will learn about new nodes that were infected. So we don't care about predicting, will you be infected 15 days in advance? You know, it just doesn't make sense. So we run it only for 6 days. And we get a very big infection rate. So almost everyone gets infected. You can imagine that if we ran it further, this thing would then slowly fall down, just as it does in all of these things. We just stopped it somewhere in the middle. And we see that our results are great. And this basically is the main reason why I'm optimistic at the moment. We see that with the general approach, we would have notified around 54, 55,000 people. Out of those, 48,000 were infected. With our additional approach, we would have notified additional 9,000 people. And out of those 9,000, more than 8,000 would be infected, which means that we roughly increased the number of detected infected cases by a quarter or something like that, which is great. Questions?
So the actual network, the real world network, would be a combination of these three models, right?
Yes.
Or it might be distributed closer to this one in some of the network.
Main problem with this model, with the Barabashi-Albert model, is that it doesn't have good clustering effect, but it has a good hierarchical effect. So there are some nodes who are very popular in this real world, it would be a person working at a store. You know, they are in contact with everyone. There is this hierarchy, but there is no clustering. But adding clustering only improves our method, only improves our performance. So I would expect for our models to be slightly better than this, but not too much better. On the other hand, you have to count in all of the noise that occurs in real world, all of the interactions that we won't manage to detect properly, all of the people who would lie about their symptoms, all of, you know, everything. But all of those problems still, all of those problems exist for the baseline method too. So we don't have additional problems. It is just a general problem that all of us have, and okay, it's just some slight randomness added to the whole model.
So these simulations that you ran here have the assumption that we can account for all the nodes. We have no hidden nodes, so to speak, infections that propagate without any apps in our example.
Yes, yes.
So is there any way that we can estimate what would be the minimum number of installed apps in a certain network that we would need to have efficiency? Have you given this any consideration?
It is very hard to say that. It can, on the other hand, be very simply calculated how much of a randomness would mess us up. Basically, how many newly randomly infected nodes, which weren't in contact with anyone, just suddenly became infected, which basically means became infected by someone who doesn't have an app installed. How many of these would have to occur daily for us to be messed up? I don't have the data here to show you, but basically the result is that it's the same for both approaches. So although I don't have a clear number, because this number would highly depend on all the parameters in real world, the number is the same as other guys have. So we don't introduce additional dirtiness. We lay in the dirt that is already there.
Right, right. And we might, I'm sorry, we might be able to estimate that within a certain network, there are, within a certain community, so to speak, there are number of people who don't have the apps and who might be spreading it.
We can do that easily. Yes, we can do that, but we can also get, you know, it's easy to calculate based on the population density information. You just know where your phones are. You can easily calculate which city has what proportion of users. And then just see how many new cases you get each day in each city and divide the numbers. Last thing that I want to go through, and then I have to go shut up, is what is the effect of parameter errors on our model? So I now said, okay, I will create this network, let's say this one, and I will say that there is a 5% transmission probability. I could have set it to 1. I could have set it to 10. I could have, I mean, it's a random number. It's a number which produces a nice looking simulation. It's not a number that is that comes from real data, because there is no real data, because that's a very messy problem to answer. In general, what we do want is for our models to be what's the word? To work well even when there are big errors in these parameters. There is a good word for this.
Tolerance.
Yes, tolerance. So we want them to be error tolerant. And the way we can model this is with the following. We have our model which we start with, very similar to the one before. We run it, we analyze its performance, and then we say, okay, I will now create a new model. This time, so I had infection probability of 5% and recovery time of 14 days. This time, I will have infection probability of 1%, recovery time of 7 days, which is a much weaker virus. This is a virus that spreads much more slower. But I will, as initially infected nodes, I will use the initial infected nodes from the previous model, so the same ones, so that I can start from the same moment and then track how these networks diverge. One which spreads very quickly, one which spreads slowly. And I will analyze in these results, I will analyze the performance compared to the real results in that previous model. So what did we do? We had one model, we infected some initial nodes, we left the simulation play out for 6 days. We said, okay, who is now infected? Then we started another model. We set those same initial infected nodes, but with completely different parameters. We ran it again for 6 days. And then we said, okay, using this simulation, how well can we predict results of this model here? Okay? And this is something that will happen to us because this is the real world and some parameters which we don't know. And this is our simulation with some different parameters. We do know who initially is infected, and we care about predicting those real infected nodes after 6 days. Okay? Make sense? Okay. So we did that. We get a much weaker infection. So initially with 5% transmission probability and 14 days of incubation, 80% of the nodes are infected. With this one, only 10% of the nodes are infected. But that ranking in risk estimates between nodes is basically the same. And when you now again sample top 40% of the nodes, you get again great results. Baseline approach identifies 5,000 out of 8,000 people who are infected, and we additionally notify 1,400 more, which is again a third of what they did.
Okay, we're back.
Okay, I was finished. So questions?
So the last simulation that you ran was the results of that were a bit unclear to me. I am not sure if everyone got it, and you don't need to go through it again. So
I think the last bit would be nice to like the very last.
Sorry, I didn't hear you well. Should I repeat the last part?
yes, just the last part where you had some sort of hybrid network, okay. I think.
So ignore the code. I will wave my hands.
Okay.
We had some kind of a network, static network. We created samples from that network so that we have some subsample for each day. This is our world, basically. Okay?
Yeah.
We took that, we stored that. Then we infected some of the nodes on day 1, on day 0. And we stored who did we infect. Okay? And now we have some setup for the virus to spread. We said, okay, this will be the virus which spreads with 5% probability, and the illness lasts for 14 days. This is a highly spreadable thing. We started from those initial infected nodes. We ran the simulation with this virus, and we ended up with some nodes being infected. Then we took the same world, same edges, and same initial infected nodes. But this time we said to the virus, you are now only 1% contagious, which is 5 times less. And you only last for 7 days, which is 2 times
shorter.
less. Yeah, exactly. And then we played it out. Of course, after these new 6 days, over the same edges, with the same infected nodes, much fewer people were infected because this is a much less viral virus. However, when we took those results and we, for each node, we said in how many of these sub-simulations, of these 1,000 simulations that we are running in parallel, with this second virus, with this weak virus, in how many of these were you infected? And we ranked them. And we took the top 40%. And we said, okay, for these 40%, we now predict that you were also infected in that first example with a highly viral virus. Okay? Then we got great results, which confirms that you don't need correct parameters of the virus. You just need enough variance. You just need enough simulations over different parameters so that all of the edge cases cancel out. And you get the real risk nodes on top, even when you have no idea what the real world parameters are.
So we took the 40% of people which were infected with less spreadable virus, and we used those to see if they still apply to the one that lasts 2 weeks.
Yes.
With a simulation that already happened, not running it again. So with
yes,
and it applies.
Yes.
Which means that we can have like a virus that we don't actually need to know the exact parameters.
Exactly, exactly. Because this is the main problem that we are facing. We don't know the parameters to simulate it. This is why all of the predictions about the number of infected cases tomorrow, all of them are wrong. You cannot predict how many people will be ill tomorrow because you don't know the parameters. It might be that in the end, we have 80% of the population infected, as in this first example, or it might be that only 10% of them are infected, as in this second. However, the risk of each node is basically the same. So if my risk is very high, then probably in both cases I would be infected. If my risk is very low, then probably in both cases I won't be infected. If my risk is somewhere in the middle, then probably in the first case I will be infected, in the second case I won't. But my risk is my risk. It doesn't depend that much on the actual virus that is spreading.
But we have some fairly substantial data about this virus, don't we?
We do, but we don't know what the exact type of interaction occurred once we detected. We don't know what the humidity was. We don't know how close two persons were. We don't know what the duration exact of the contact was. We don't know if someone spitted in someone's face. You know, all of these details.
Yes, we do have the duration.
Okay, but I mean, you know, it's whatever we have, we can use to increase the chances of getting it right. The main thing is that, and the main critique of Harald and all of them was you cannot run simulations because you don't know the parameters. And I was trying to explain that you don't need to know the parameters because you don't need to run the exact simulation because you're not estimating the number, the total number of infected cases. You're only estimating the risk of each person. And the risk of each person is really mostly encoded in the topology of the network. It's not encoded in the actual virus that is spreading. Of course, there is some correlation between who gets infected and what the virus is. There is no, it's not a surprise that Ebola got so spread around Africa because there is vomiting, there is diarrhea, there is, you know, and there is not the proper infrastructure. It is no surprise that the coronavirus is so spreadable now that everyone is flying on planes. But in general, you know, the most important thing is your location in the network.
Right.
Anyone else?
So just to clarify, in the end, we're going forward with a model that's a combination of the ring clustering and then also just the normal node network. Is that right? Instead of using one or the other specifically, we're combining the two.
I lost the sound for a second. So what we use our model, and we use also direct contact tracing, if that was the question.
Okay, so we're using both. That was sort of the question.
Yes, yes.
Okay.
We use both because I would say that it's unethical to not notify someone who was in direct contact with the infected person.
Right.
If they were in direct contact, they should get a notification no matter what the model says. But the model will say that they have a high chance anyway. So it's not really important. We can only use our model, and just naturally all of the first neighbors of infected nodes would get notified. But just to stay safe, we hard code that as a rule.
Okay, I think that makes sense. Thank you.
Anyone else? Okay, I think that's it then.